In section 1.4, we're going to learn about our first big calculus topic, and that's called limits. So this first video, we're going to focus on graphical limits. So in essence, limits are the height or the y value of a function. So limits are the height or the y value a function approaches as you follow the function's x values. And when we talk about following the x values towards a specific given number, it's going to be from both directions. So from both right and left. So we're going to look at, well, what's the y value as x approaches, let's say, 2? So from both directions approaching 2, what happens to the function's y value? That's really visually what a limit is doing. So the notation for a limit, you'll see limit and underneath it, sometimes you'll see it like off to the side as a subscript, but it's just the limit as x approaches c of f of x is equal to whatever the y value is. So that capital L is really a y value. So the limit as x approaches c, so c will be some number, and then f of x will be the function. Usually you'll see the function right there written out, the equation for the function, equals, and then whatever you end up with. So that's the notation that you'll see. How to do this, so there's some steps here to write down. So I'm going to kind of start up top here so we have enough space. So the first step is draw a vertical line. Through the x value of c. So through x equals c. So basically whatever the limit is approaching is what the value you'll want to draw a line through. Now this is going to end up being very easy for you once you get the hang of it. It's a little odd at first, so that's why we have these steps. What'll end up happening is you won't really need to actually draw the vertical line. You're going to actually just be able to figure it out. But for right now, we're going to go through these steps just to make sure that it's clear. So then once you have that vertical line, you're going to trace the graph, so the function's graph, towards the vertical line. From the right. And when you hit the line, I'm going to say when you, oops, I just wrote twice. When you hit the, I'm going to actually say the wall, meaning the line, but we're going to kind of treat it as a wall. Mark it with an X. And then you're going to do the same thing, but from the other direction. So we'll do the same thing. So repeat from the left side. And then lastly, the limit will be the y value that has the x on it. So the limit is the y value where you marked the x. So we're going to try this, doing this step by step, but like I said, you don't have to show the vertical line and show the x. You'll be able to go right into just finding the answer. So I'm going to have to kind of move the screen up and down here to be able to see, but for the first one here, so we're going to look at all the parts for number 1. So there's a difference in notation. So the ones that have F, that is just asking you if 1 is the input, what's the output? So this is just what we did in the beginning of chapter 1. So not really a calculus type thing. So if I input 1 into the function, so if x equals 1, what's the output or what's the y value? So that means I'd go to my graph and I have, here's my function. So this is function f of x, this blue. So if I have an x value of 1, what's the output? What's the y value? Well, the y value has to be a point on the graph, which happens to be 1 as well. So that means the output is equal to 1. If I look at part C, then we'll talk about the limit. So if I look at part C, if the input is -2, so x value is -2, what's the y value? I go up to the y value, it's at 4. So that equals 4. And then f of 0, so 0 is the input. What's the y value or what's the output? Well, it's just going to equal 0. So that's nothing new. That's not a limit. But we're doing that just to kind of compare um, limits to inputs and outputs of functions. So I'm just going to write next to this that this is the output. So now let's look at actually following the steps for finding the limit. So for part B, the limit as x approaches 1 of function f of x. So notice that the x going to 1 or approaching 1 is not under it, it's next to it. Same thing, just again, different. You'll see it both ways. So if we look at the limit as x approaches 1, I'm going to go to 1 on my graph. X equals 1. I'm going to draw a vertical line. I like to do a dotted vertical line just because it's not really part of the graph. It's just we're kind of creating this wall to look at. And then what we're going to do is we're going to approach x. So we're going to trace the graph and go to 1 from the right-hand side. So approach from the right-hand side, and then we mark it with an x. And then we're going to trace the graph from the left-hand side, and when we hit the wall, or we approach 1 from the left-hand side, we mark it with an X, and we notice that it's at the same spot. It won't always be, but for right now it is. And the limit is the y value. So as we approach 1 from both the right and the left, the y value of the function is 1. Now you're noticing maybe that was the same answer as part A, which most of the time will be true, but we're going to see it won't always be true, and we'll talk about how to handle that. So if we look at the part D, draw our vertical line at -2. So draw a vertical line through -2. Approach the limit from the right, so trace the graph from the right until we get to the wall. And then approach the graph from the left, or as x approaches -2 from the left, get a wall. Notice that we get the same answer as what we had before. Again, won't always work, but sometimes it will. So now we do our last one here as x approaches 0. So I'm going to go right through the middle here, x equals 0. And we're going to approach from the right-hand side, so tracing along that graph until I hit the wall, tracing the graph from the left-hand side till I hit the wall, and again, we end up with 0. So there's finding the limit. That's essentially all it is. And like I said, you don't have to draw these vertical lines in there. You don't have to draw the x's. You're going to be able to just say, okay, I'm doing the limit as x approaches 0 of f of x from the right, and I end up here, and then I approach it from the left until I get to x equals 0, or as I'm approaching 0, I should say, from the left-hand side, and the y value is the same. It ends up being 0. So you're going to be able to do that without having to run through those 4 steps from the middle section of our paper. So let's try number 2. And actually, what I'd like you to do is pause the video, try number 2, and then unpause, and I'm going to go through it. That way you can just kind of see if you got the hang of it. So go ahead, pause the video. And hopefully now you've tried the problem. So once you're playing this again, and let's go ahead. So I'm going to just go through these a little bit quicker. So g of -2, so I go to -2. My y value is going to be 1, so that's just going to equal 1. The limit, so again, I can think about, well, here's -2, so I'm not going to draw in that vertical line, but as I approach from the right-hand side, I'm at 2. As I approach from the left-hand side, my y value is still at 1. I think I said 2. But as I approach from the right, the y value is 1. As I approach from the left, the y value is 1. So that's just going to be 1 as well. G of 2, so I go over to 2, x value of 2, y value is down at -1. I'm going to just write this -1 there. So -1. And then again, drawing in the vertical line. You don't have to draw it in. If you want to, you can. As I approach from the right, I'm at -1. As I approach from the left, I'm at -1 for a y value. So again, it ends up being the same thing. And then g of 0, so I go to um, my x value of 0, and the y value is also 0, or when I'm at an x value of 0, the y value is not 0. The y value is up here at 3. So that's going to be 3. So equals 3. And then when I go back to the origin here and I'm looking at x equals 0, I'm approaching from the right-hand side, the limit is 3. As I approach from the left-hand side, the limit is also 3. Y value has to be the same. And I should have had this labeled, but this function here is g of x. And of course, we used that the whole time, but we really should have had it labeled. So let's go ahead and look at some exceptions. So again, we saw on examples 1 and 2 that the input and output of the functions were equal to the limits of the functions as x approached those same values. So let's look at a situation where that doesn't happen. So if we look at the next page, we see that there's a graph where it looks much different. So one thing to point out here is this graph is not continuous, meaning there's lots of breaks in the graph. So one thing I want you to notice though is that on the left here, this keeps on going forever. So there's really an arrow, or because it's going to the edge of the graph, we can say that that keeps going up. Same thing with this one. And then same thing with the right. So since those pieces are drawn to the edges, we're assuming that they keep on going. So that means we have some breaks in the graph. So see how we basically trace, there's a hole here, there's another point, then there's a spot where we have to jump to continue to the function, and there's another hole, we'd have to jump up to this point to continue. So this function is not continuous. So this means that we might run into some issues. So if we look at going through these problems, g of -8, so go over to -8. When we talk about evaluating a function, it has to be where there's a filled in point. So that's an important idea. So when you evaluate a function, you must use a filled in point. Or basically like part of any of the curve here, anything on that curve is considered filled in. So when I'm evaluating a function, if I go to -8, I need to actually use this point here, not the open circle, because the open circle represents that it's undefined at that point. So since I have it filled in at -8, there's a point right here, that means that the y value, or the output, is actually -3. So this is going to be -3. Versus if that filled in point wasn't there, I would say that the function is undefined at -8 because there's no point. But because I have that point, I can say, well, the y value has to be -3. So then when we think about this in terms of the limit, so now you draw in your dotted vertical line. Again, you don't have to draw this in, but you can. And we start tracing the function. So as we trace from the right-hand side, so basically coming from this curve here, as we approach -8, we end up right here. As we approach -8 from the left-hand side, again, our x is down at -6. So our limit can be on an open circle because the limit is not really at that point. It's as you get close to that point, what are the y values approaching? The y values are tending to get towards -6 as we approach -8 for the x values. But at the point -8, well, then that's where the function's defined. The y value would have to be -3. But the limit is as we approach. So it's what is the function tending to do? So for limits, you can use open circles. So may use open points. So if we look at another example, so g of 6, so we go to 6, again, cannot use the open circle for evaluating. I have to use a filled in point. So this is going to be 5. And then if I approach the limit, so now I'm going to draw in my dotted line again. So from the right-hand side, we're up here at 5. And at the left-hand side, we're down here at 2, it looks like. So now we're seeing that the limit could actually be 5 or 2. So I'm going to just write that. And really what that means is the limit can't be two different things. So this is a situation where you actually say, well, if you end up getting two different limits out from the right hand or the left hand side, this is where we say the limit does not exist. So anytime you run into a situation where you have two different answers, the limit does not exist. So I'm going to just write does not exist. You're going to see DNE a lot. So feel free to use that abbreviation. You can use it in XYZ homework as well, for does not exist. So that's a very common notation. And then if we look at the next example here, g of -2, so I go down to -2, g of -2, well, this right here, there's actually, this graph isn't actually going to cross -2, so we're going to use this point right here. There's kind of like an asymptote here almost, where this would just get really, really close to -2. So the function at -2, the y value is going to be 3. And if we look at the limit, so again, looking at this, if we go from the right-hand side, this limit, as we get to -2, is just going to keep on going up. It's not going to ever really get to a y value at -2 because it's going to get really, really close to this asymptote. So this is what we would call going up to infinity, or you could just say does not exist. So I'm going to say infinity is what the y value is approaching. It's just going to keep on going up. And then from the left-hand side, as we approach -2, the y value is right here. It's going to be at 3. So again, we have one side doing one thing, the left-hand side doing something else. So we would cross this off, and again, this would be a does not exist situation because our limits from the right hand and the left-hand side are not agreeing. So if we look at this question here, so does the function's value at x equals c necessarily equal the function's limit as x approaches c? So this is basically asking us, are these two things always the same? So when we evaluate a function at a point, is that the same thing as finding the limit at that point? Not always the case. And if you remember the first page, we saw that examples 1 and 2, when we evaluated as x approaches, or when we evaluated at x equals some number, and then we evaluated the limit as x approaches that number, the values were always the same. Not the situation here, not the case. So basically, I'm just going to say we have lots of different scenarios where the limits and evaluating the functions are not the same. So I'm going to just say no, look at examples, let's just say 3a and 3b, or you could say 3c, and 3d, or 3e and 3f. We're seeing it in all the situations where the limit and evaluating the function are not the same. And then this next thing is, what new problem did we encounter when finding the limits for 3D and 3F? Well, we got two different y values. So we found two different y values when going from the right and the left, which leads us to this next concept. And if you heard me saying it, I kept saying the left-hand limit and the right-hand limit were not the same. So that leads us to, well, what happens if we want to specify which direction we're finding the limit from? Well, then individually, like the left-hand limit might exist while the right-hand limit doesn't, and overall, the limit from both sides does not exist. So if you look at this notation here, this first one, where see how it has a little negative after the C? that means you're coming from the negative numbers. That means you're coming from the left-hand side. So this is called the left-hand limit. So this means you're coming from the left, you're coming from the negative numbers. And notice that it's like, so if it said x is approaching -2, there would be another negative on the end to represent it's coming from the left. This one is called the right-hand limit because it has the positive after the number. So it means it's coming from the positive numbers. So it means it's coming from the right-hand side. So that's the notation that we'll use to specify. So this theorem here is a fundamental idea where as long as the left and right hand limits are equal, well then the limit has to equal that same y value, the limit from both directions. So whenever we see the limit as x approaches some number, you have to consider it from both directions, and all three values have to match up in order for the limit to exist. So that will be true for any type of graph you see, including, we saw it in examples 1, 2, and 3, where some of them were equal, some of them weren't. So if we go back and we rethink about what we did up top, so the limit as x approaches 6, this would be from the left-hand side. So when we approach 6 from the left-hand side, so just kind of looking back at this example, approach 6 from the left-hand side, we end up with 2. As we approach 6 from the right-hand side, we ended up with 5. So I'm going to just write those down here. So this was equal to 2 from the left-hand side. It was equal to 5 from the right-hand side. Overall, the limit does not exist. However, the individual limits from the right and the left do exist. So just be careful what the question's asking for. Is it asking for the whole limit, or is it asking for an individual part from one direction? But anytime you see it like this, x approaching 6, it indicates both directions, the right and the left. Those have to be equal in order for you to have a limit that exists. So if we look at the last section here from -2, or as x approaches -2, so from the left-hand side, we got 3. From the right-hand side, we have infinity, or it does not exist. It doesn't really approach a number because it just keeps increasing. So for this, it would be 3 was from the left. This one was infinity or does not exist. XYZ homework likes you to write does not exist instead of infinity. Like on a written test, either would be fine, but I would just do does not exist. I would just get into that habit. And then overall, the limit as x approaches 2 from both directions does not exist because these are not equal. So there you have it. Is so just kind of going through and doing limits on a graph. And then the next thing we'll talk about is how to do these without a graph. So how to do these algebraically.